Welcome back to CS 194. We're going to continue today in this asynchronous lecture talking more about CUDA programming for GPUs, and specifically going to focus on shared memory and how you use shared memory in CUDA. So this will be some similar ideas to what you saw in OpenMP in terms of how you share memory across threads in OpenMP, but will be somewhat different. We have to manage the memory a little bit but more explicitly in CUDA in order to get shared memory. So just to start out with, let's review what we've talked about so far. First of all, CUDA has a hierarchical parallelism model. And so when you launch a kernel, which is the way you start some computation on a GPU, you're launching a grid of blocks. And within that, within each of those blocks, there are a set of threads. And at the call site, at the point that you're launching, the point in the program where you're launching the kernel, you specify the number of blocks and the number of threads with this triple angle bracket notation. So the other thing to be aware of is that there's a maximum number of threads you can have per block on GPU. And that maximum on the V100 using the current version of CUDA is 1024. There's actually 512 on many of the earlier GPUs and the earlier CUDA versions. So that's one thing that will limit how we write our programs, is that we can't make the threads number larger than 1024. Now, another review is we talked about, given this hierarchical parallelism, if you've got an array, the array is going to be spread out over all of the threads and all of the blocks in the grid. And so you've got an array, say a one-dimensional array that's declared in a kernel, you get this kind of one-dimensional, you get this layout of the array. So if you want to figure out which element of an array a particular thread owns, as response it has affinity with, it's given by this expression that says, well, it's your thread ID, which is your thread ID within whatever block that this thread happens to be in. And then you have to add to that the block index that you're in times the block dimension. So that'll give you a global index into one of these arrays that's spread out over all of the threads. And finally, and I talked about this only briefly, so we'll talk a lot more about this today. We talked a little bit about the fact that there's both per thread local memory and there's also per block shared memory. And the per thread local memory we can think of as being registers. There's actually a lot of registers on these GPUs, as there's a lot of threads and they each need a set of registers. And so that would be some thread local memory. There's other kinds of local memory, and I'll say a little bit more about that. But there's also then per block shared memory, which means that all the threads within a block can see that shared memory together, but other blocks that are executing within the kernel cannot see that shared memory. We didn't need to really worry about this, which is why I didn't talk about it too much for vector addition for that example. And that's because in vector addition, all you were doing is adding up corresponding elements of two arrays, two vectors, and then putting the result back in that same location in one of the vectors. And so you didn't need to share any vector and any data, even read-only data. You didn't need to share anything between the different threads. Each thread was just reading one element of one array, one element of another array, adding the two together and writing it back into that one of those two elements in one of the two arrays. And so it didn't require any type of shared data to make this work. So we'll look at a different example today, which is a 1D stencil example. This is just a simple example in order to give us some idea of how we would use shared memory. So in this a 1D stencil example, I've mentioned this before in a much earlier lecture, talking about the fact that in something like machine learning algorithms where you're doing convolution, so convolutional neural nets, you're sweeping over something like a two-dimensional image and looking for a pattern. And you do that by taking a little block, a little 3x3 block, and looking for a certain pattern in that block, looking for a certain set of colors in that block, or whatever it is, depending on what that filter looks like. And we can do that on a one-dimensional array. So you could think of this, if you wanted to, as just a one-dimensional array of pixels where we're looking for a certain pattern. In this case, we're not really passing a filter over it. What we're going to just do is something even simpler, just to make the code simpler, which is to add up a set of elements within one array and put those into the result in the output array. So in this case, we have a 5-point stencil. And another way of saying that is it's a stencil with a radius of 2. That means that we've got one element that we're updating, and we're going to use that one from the input, and we're going to also write that one in the output. And then we've got in the input, we're going to access 2 to the left and 2 to the right. So that gives us the radius of 2. So overall, there's 5 points involved, 5 array elements that are involved in a 1D 5-point stencil. And we can do these stencils, as I said, in 2 dimensions. You can also do them in 3 dimensions. They come up all over the place in scientific computing, in addition to machine learning. For example, things like climate modeling and other places, you'll see a lot of these different kinds of stencils, sometimes much more sophisticated, or generally more sophisticated than what I'm talking about here. So in this simple case, though, we've got an input array that has 5 ones and then a 10 and then 5 more ones. And we're using this simple stencil example that just says, add up the 5 elements and put the value into the middle element. Then we get on the first thing that we can compute is the 5. The 2 ones just carry forward from the input array because they are not, that we don't have, 2 elements to the left of them. There are other ways that you can handle boundary conditions that come up on all these different problems, but for now we'll just look at it that way, and then we'll just leave those as the output. And then the next one picks up the 10, and so the output value in that fourth spot is, or index 3 is 14, and similarly there's a bunch of 14s then in the middle as you go through it, 1 more 5, and then the 2 ones that are at the end. Okay, so in this stencil example then, the way we're going to think about parallelizing it is assign a thread to each one of the elements of the output array. And that thread is then going to need to read depending on how wide our stencil is, what the radius is, it's going to read, say, 2 things to the left and 2 things to the right of that element. We can find which element it's going to be computing on by using one of those block dimension sort of expressions. Each block is going to have, this block dim number of elements per block, which will be specified then at the call point. But we're going to try to write the code inside of the stencil operation, which doesn't depend on a particular constant value of the block dimension. It can be passed in. And then we'll look at the input elements. You should notice in something like a 5-point stencil are going to be read 5 times, because you'll read it once in each one of the positions here as you slide the stencil along through the array. Or in a 7-point stencil, you're going to read each one 7 times. So you're going to be reusing the inputs, and that's something we'll want to take advantage of by using some shared memory. So what does shared memory look like in a little bit more detail on a GPU? So within a block, as I said before, the threads can all share data that's in this shared memory. Shared memory on a GPU is very fast on chip memory, but it's user managed. That means we're going to have to put things into shared memory. So you can think of it sort of like the L1 cache that's on chip, except that in a multi-core processor or a sequential processor, the hardware is handling the movement of data from, say, DRAM off chip to your fast on chip L1 cache. Whereas in the GPU, and by the way, there are caches as well, but what we're going to have to do is to move things explicitly into this fast on-chip memory, which I think I've referred to last time, at least in one of the little examples, as a scratch pad. So we could think of this as a scratch pad. We're kind of moving things in and out of it explicitly. And we do that by declaring data structures in that fast memory, that shared memory, as __ shared. The data in this region, these underscore shared data structures, is not going to be visible to the threads in the other blocks. It'll be private to the block, but it's shared to the threads in the block. I find this terminology somewhat confusing because there's all these hierarchical parallelism. So it's shared at one level and private at another level, but that's what it is. And that's the traditional terminology here for GPUs. So just to give you a more complete picture of all the different types of memory on a GPU, and most of these are explicitly, or all the ones that I'm showing here are really CUDA aware. That means things that are visible to the software level. So not hardware managed caches. And that we've got our threads in here. This has little two-dimensional indexing. So we've got block 00, thread 00, and thread 10 inside of that. And each one of those has its own set of private registers. Those are very fast. So you can normally access a register in 0 cycles. And then, but there's 256 kilobytes on this whole GPU chip of the register set, the register file, which is all the registers that are there. So there's actually a fair amount of memory, and it's a fairly expensive piece of hardware. It's all, as I said, also very fast. Now, the other thing you have on the chip is this shared memory. And that's, up here, all of these red things that are above the threads are very fast. This shared memory, though, is not private to a thread. It'll be shared by all the threads in a block, not shared across the blocks, as I've said before. And I think the next thing we'll say is, yes, this is how much shared memory we have. So it's pretty fast access. And this is the focus of what we'll be talking about today. On something like the B100 is 128 kilobytes of shared L1, that's actually shared with an L1 that I'm not showing here. You can kind of configure how much you want as to use in this as this explicitly managed shared memory as opposed to an automatically managed cache. Why do they do this? Because if you really want a very lightweight processor that runs very quickly, you make things as simple as possible, and you don't make the hardware manage the memory hierarchy. You do it in software. You make the programmer do more work. There's other levels of the memory system that I'm not going to really talk about, but you should just be aware of them. There's something called a constant cache that is also shared by the threads that you can put in variables that are not going to be changing, that are constant. There's also a texture cache that's shared by all the blocks. And that's fairly small, but it's something that's that can also be used to share things now across blocks. And then there is global device level shared memory as well. These are going to be much slower. So the local, these local and global things. So although it's called local and it's logically associated with one of the threads, it's really physically really more like part of the global memory. So it's going to be slower. And these are on the order of 100 times slower, so really significantly slower. Okay, so what's our parallelism strategy? Well, we're inside of this, we're going to use both blocks and threads. And this is typical of most of GPU applications. You could have written, and I think we showed the vector addition example using either threads or blocks. It didn't matter very much because we weren't sharing memory between the threads. But why are we going to use both of them in an application? Well, we can't use all threads because there's a limit on the maximum number of threads per block. So threads alone aren't going to work if you've got an array that's larger than 1024. We're also not going to use only blocks because we can only get access to this fast shared memory if we're operating between threads. So we could still share some of this slower memory between the blocks, but we don't want to do that for things that we're going to share quite frequently. So we'll use a combination of threads and blocks in most applications. Okay, so our GPU thread strategy here for our 1D stencil is we've got our output array, and we're really going to divide it up in this kind of owner compute strategy, which says each thread is going to own one of the elements of the output array, and it will be responsible for computing it. So, but we'll divide the output array into blocks, and each one of those blocks will be assigned to a thread block. So, and then within that, each one of the elements is going to be assigned to a thread. This will really happen automatically in terms of the way CUDA will lay out that array. And then each block is going to compute blockdim.x output elements. And it's going to then write those blockdim output elements into some global memory so that they're accessible outside of this kernel. So, and then we can do we can move them back to the CPU, for example, as we talked about last time, moving data back and forth to the CPU. So this is the way the output works in terms of the parallelism is very similar to what we did in vector addition. What about the input? Well, because of the fact that you are going to reuse some of these values, we're going to load the input values into the shared memory so that each thread doesn't need to have its own copy of all of those, say 5 or 7, in this case 5 elements. So this is one with a radius of 2 is shown in the picture here. So what does that mean? Well, what I'm showing here is a picture in which the output array, so the second one of the arrays here, the middle section of the middle block, which happens to have 8 elements. This is a small number of threads to have, but it fits on the slide. So those 8 elements correspond to 8 threads. And what do those 8 threads need in order to do the computation, in order to evaluate those 8 elements and fill them in? It needs the 8 elements that correspond to that from the input array, and it also needs 2 things to the left and 2 things to the right. And so these are often called a halo. And so this is a halo of the size of the radius at each boundary, at the left and the right boundary. If it were a 2-dimensional problem, we would have a halo that goes around it, and on the top and the bottom, as well as the left and the right. And we also often call these ghost regions. So they're going to be copies of things that other processors, other blocks in this case, are going to need, but we'll have a copy of them for this block. Now these are not being updated. This is the input. These are just going to be read, but they can now be shared and read only once into the GPU, into this fast shared memory, and then accessed quickly by all the threads in that block. So in order to keep track of this now, what are we doing? So we're writing code for a block, and that block is going to have a global index into the output array. So that looks just like the example that I showed earlier. So this first line here, the GPU kernel is going to compute 1 element in the global output, and that global index, the pointer into it, the integer that says my thread is responsible for this particular element, is this G index, and that's going to be the thread ID within the block, right? Plus the block ID times the block dimension. So that'll give us the global index. And now the input, though, has been copied into shared memory. That will give us a local index. We need to index that with a local index because that's a much smaller array. And you might think, well, it's just the thread index, which that's not quite right, because we've padded it to the left and the right with the these halo regions of size radius. And so we need to then use the local index, which is the thread index plus the radius, which is the 2 things on the left that are going to shift our index over by, say, 2 in this case. All right, so here's the code. We'll start with this is a global function, so it's going to be something that we can call as a kernel, the Stencil kernel. We can call it from the CPU. It'll run in the GPU, so that's where the underscore global keyword comes in. And it's taking in an input array and an output array. And it's going to, then it needs to make up a temporary array to store some piece of the input array. And that is going to have the size block size, which will be whatever we pass in as the block index, but this is going to be a compile time constant, plus 2 times the radius. So that's to give us the space for the 2 elements on the right, however, the radius on the right and the radius on the left we'll have, so that's why we have 2 times the radius plus the block size. And the key word in here, underscore shared, says this is an array that I want to be put inside of this fast shared memory that's shared by all the threads in the block. And you can also have scalars, non-arrays that are put in shared memory. That might be useful if you have a constant value that you want all of the threads to see. In this case, though, it's going to be, or maybe you've got some kind of a variable that you're going to access, say a counter, then you're going to have to be careful about how you do that in terms of synchronization. But in any case, this is going to put this temp array inside the fast shared memory. Okay, then we compute those 2 indices, the global index and the local index, which I talked about previously, to point into the global array, the in array and the out array, but also into the temp array, which is the local index, the L index. So we need to actually copy the elements from the input array into the temporary array in fast memory. And so the first thing that we do is we copy all of the things that are the non-halo regions. And this is just saying, well, any thread is going to be living sort of at one of those elements of the output array, one of those elements of a particular block of the output array, those threads are, and so they'll copy something from that global index into the spot in the local index. Now that's filled in everything except the halo regions. So in order to fill in the halo regions, then we say, well, if I'm a thread that is down at the bottom, and this is just one way of filling this in, it may not be the most efficient, but if I'm one of the first, say, 2 threads, so thread 0 or thread 1, if I've got a radix of 2, then I'm going to execute this code in the conditional. I'll say, well, take my local index minus the radix. So it'll say go back to the 0th element if I'm thread 0, and my L index was computed to be 2 because that was leaving space for the 2 things on the left. And so I subtract that and I fill in the thing on the left, and I use this global index also shifted by the radius, and that in order to figure out what value it's supposed to be filled in with. And similarly, I'm going to also fill in the thing that's on the right end, which is the one of the things, at least on the right end, which is, and sorry, this block size is right there. So this is just giving us the global index sort of at the other end plus the block size, and then writing in the writing it into the place in the temporary array. So that's filling in 2 of the elements, one on the left and one on the right. And because all of the threads that are less than the radius are executing this, all of the elements to the left and the right will be filled in by this code. As I said, you could write it in a different way where you had, say, other threads that were executing the things on the right than the left, but this is maybe one of the simpler ways to write it. This is not all of the code. So the rest of the code is on the next slide. And so here's just the header again. So this is this global function that we can call from the CPU. And this is the comment says that all the code that was previously on the previous slide is still here. So how do we now, we've filled in the temporary array, and we can now apply the stencil. We'll initialize the result to 0 and then execute this loop that says for the offset equal to from the minus radius up to the radius. So we're going to go from, say, minus 2 up to positive 2. So we'll have 5 different values we'll look at here. And we'll take that offset and add it to the local index. Remember, the local index pointed to the particular result, particular element that my thread was assigned to. So I'll be looking 2 to the left and 2 to the right, as well as looking at your own value by running this loop. So this is just a little loop that's running from just over the stencil itself, the filter itself. And then once we're done with this, we will store the output values into the, we'll store the result into the output array. Okay, now there's a problem with this code. There's a race condition because I'm filling in the temporary array by reading the input into it. And you've got a bunch of independent threads that are doing that. They're not running in lockstep or anything. That is, they're not running exactly the same instruction at the same point in time. And so some of them can run a little bit faster than others. And in particular on the GPU in this case, some of the threads are executing this conditional. Remember the conditional that's filling in the halo values. And so the threads that are doing that are going to get a little bit behind. So thread 0, for example, is not going to start actually computing its value or getting to that computational step until a little bit later. And so the effect of that is that, for example, you can have thread 0, it's filling in sort of its own location, which all of the threads are doing. So one of these this first blue value here, then it's writing the leftmost element here in the, and then it's writing the rightmost element or -1 here. And then it's, but it doesn't do that right until T7 actually goes and tries to read that value. And so you're going to have this problem, which is that the thread 7 is trying to read the value before you've actually filled it in with the value, because it's looking at the temporary array that hasn't been filled in yet, at least for that index. Okay, so that's a problem. And we solve it the way, at least one of the ways that we solve things in OpenMP, by putting in a barrier. And the way we spell barrier in between all of the threads in a block is to say sync threads. And so this void method that returns this underscore sync threads is something that is going to just is going to block and wait for all the threads to get to that point in the program. And it's used to prevent all these different kinds of hazards that we've talked about before: read after write, write after write, write after read, and so on. So all the threads in the block have to reach the barrier, and you do need be a little bit careful that if you stick one of these barriers, and this is true, by the way, of barriers in general in any of the parallel programming models we look at, if you put a barrier inside of a conditional, you want to make sure that all the threads are going to execute that conditional. Otherwise, that go down the same branch of the conditional, or some of them will be executing the barrier and the other will not, and they will get stuck waiting for the other thread. So at least that's something you didn't need to worry about in CUDA. So we can fix this code now, and I haven't again shown all the code because it would just get too small to show here, but there's the initialization code was up here in the comment that I haven't shown. You stick in the sync threads and then you do the application of the stencil, and that should fix the race condition. Notice, by the way, I did not put a synchronization point after the computation of the stencil and before writing the output. That's because if I'm thinking of myself as a thread, I'm going to have computed this particular result and then before it gets used. And so there's no problem with other threads trying to read this result or use this result before it's been computed, because just that thread is computing that local. In fact, that result, the result variable is probably going to just be sitting in a register. It'll be a register value and not accessible by the other threads. The registers, by the way, are managed by the compiler, just as they are in most in a serial program, going back to Unit 1, where we're talking about optimizing things like matrix multiply, and whereas on a shared memory multiprocessor, the levels of cache are handled by the hardware, but in both cases, the registers are handled by the compiler. Now, you learned that you can sometimes coax the compiler to do other things in terms of what it puts in the registers by writing certain types of code or maybe putting in certain kinds of hints and things like that. But nevertheless, it's really the compiler that's moving things in and out of the registers. And that's true on the GPU as well. What's really different about the GPU is this, this shared, I have to go back a few slides here, but the shared keyword there that I needed to use in order to say, I want to put something into fast memory. So that's not being handled automatically by the hardware or by the compiler. Okay, so let's see. I think there's my kernel. So that's really all I wanted to talk about today. And this hopefully gives you enough to get started on the homework, as well as getting started on the lab assignment for this week. And so just to summarize, though, you've seen the global keyword, which is a way of telling CUDA that this is a function that you want to be callable. That is a GPU kernel that's going to be callable from the CPU, but will run on the GPU. You also have seen the shared keyword, which is a way we just saw today, a way of declaring a variable that lives in shared memory that's shared by all the threads in a block. There's also data that's shared between so this data, is shared between the threads in the block, but not visible to threads in the other blocks. And then you saw the synchronization as a barrier. And we've also talked about, which you may need to use as some of this other, this other memory space, for example, that you're copying things in and out of. That'll be slow, so you don't want to access it frequently, but that is something that you can access between the blocks as well as between the threads. So hopefully that gives you an idea, and I'm sorry I can't be here in real time to give the lecture this week, this Wednesday, but I will be back on Monday, and we will see you all then. Thanks very much.